Hello, I'm Richard Eastis. I'm the PI for the Gold mission. I'll be talking about the observations by what, in my slightly biased opinion, is the most important mission NASA has flown in the past decade. The key points, I'll talk about a few of them here first. The mission had a prime mission of 2 years. That ends in October. Early this month, in June 2020, we submitted a proposal for extended mission. The instrument's healthy. It's being closely monitored, more closely than we had initially, because we realized the gain was the source of some uncertainties, or changes in the gain throughout the day were sources of uncertainties in the 1356 mission. We've been, since the beginning of the mission, following a nominal daily schedule of observations and having some occasional campaigns. The status, the data processing is what's happened is there are very few gaps in the coverage. Typically, the last few months, we typically have the data available within about a week and a half. At least that's the L1C. The L2 is usually like a week or two after that. It's available. Just briefly about the observations, since there may be some people in the audience who are unfamiliar with the mission. I'm sure everyone else remembers all these details. Disk scans are most of the observations. Most of the time is spent on disk scans. The night side is only partial disk scans, just to increase the signal to noise. Those are done in the latter part of the day, each day. Earlier in the day, there's full disk scans. They are occasionally, they're at 30-minute cadence, but occasionally, every 30 minutes, there's a period in there where a limb observation is done. It typically is a limb scan. Occasionally, it's an occultation when there's a star near the horizon. Okay, now we get to the main event here. Let's do some science. The things in blue here are, I'll be discussing those. Some of the things in black, there are papers in the special JGR section on gold. Some of these other things, there are papers coming out that are in blue. There's the O2 densities, there is a paper out on that, but I find it's really intriguing observations and I like to talk about it. The mesosphere-thermosphere wave coupling, Quan has a talk about that, CEDAR talk that's recorded, so you can catch that separately. So anyway, there's some nice results there also. Now the nighttime, this is the thing that was most striking initially. Large-scale changes are much more dramatic than I'd ever appreciated from looking at ground-based observations from one location throughout a day, or from a LEO satellite, which makes a pass and cuts through the equatorial ionization region every 90 minutes or so. We scan, do the partial disk scans near sunset, just after sunset. Initially at night, there are only one channel is used. It scans alternating north and south latitudes. So that continues until late at night, when both channels are used to do the disk scans, partial disk scans. So, and those disk scans by both channels continue for about an hour and a half each night. The region scanned is about 45 degrees longitude near sunset, and so that gives about 5 times each night a geographic locations observed. So you can observe both crests repeatedly throughout the night, at least when there are two. Occasionally, there's only one. Now, I'll just highlight here one of the things that is coming out, some work that'll be being done by Deepak, will be in JGR special issue. The observation has been mapped into geomagnetic coordinates You can see the bubbles, they stand out prominently here. And since they're observed on repeated scans, they can be tracked to the change in position, giving the velocity through change in longitude versus time. Some really, really nice results there. Some fabulous results. So it's really interesting to see that. Also, there's a recent paper by Joe Huber and Hanli Liu that used the SAMI and Wacom-X models to do some modeling of the bubbles, and that's in GRL. That's just recently out. All right, now, of course, the geomagnetic storms, everybody's always wanting to look at those. There are lots of interesting things happen. This 800-pound gorilla, maybe it's only 700 pounds at solar minimum, because even though there's no big storms, there's still significant changes from the relatively small storms at solar minimum. The gold observes the T-disk every day. So the storm day, this is a relatively small storm in 2019. Temperature is shown here. And by taking the difference from the previous day, we can see how much the storm really changed the temperatures. And it's pretty dramatic how much change there is in the temperatures. It's also shown here is that the composition, they have this really dramatically different structure and more focused structure than the temperature changes. So it's all very sort of being able to follow this is something we've never been able to do before. The data that I'm showing you here is slightly different. It is different. It's coming to the website this summer later. The T-disk data is always, we always thought it was the most challenging of the measurements gold makes, at least as far as the requirements we had it set up for ourselves with NASA. The products identical to this will be out later this summer. The stuff has been, the data has been 2 by 2 before the retrievals. You don't get quite the same results if you sum up the 2 by 2, the current stuff, because there are other changes we also made to improve the data quality, decrease the uncertainties. Statistical uncertainties in this, that stuff I'm showing you, at least for the temperatures, the T-disk temperatures, is about 60 K with a 30-minute cadence. In addition to the binning, one of the changes we made that really improves the data, decreases the uncertainties, is in the temperature retrieval process. We've looked at that enough now that we realize we can make some changes to how we're doing it. So the way we get the temperatures, the T-disk temperatures, is we use fits to the N2 LBH emissions. We retrieve it by looking for our best fit. Now there's 7 vibrational levels in the LBH bands, and since the brightness of these can vary independently, we know that in the aurora that the relative populations, the amount of emission from each of these vibrational levels is different than it is in the day glow. Since we know that they can vary, we've had those as independent parameters. Because we know that the pressure varies with altitude. As pressure varies with altitude, the emission varies with altitude, the balance of emissions does. We just didn't have a confidence that initially anyway, that we understood the populations well enough to set a value for those, but without retrieving it. So we've been retrieving those. Part of the issue is shown here as the solar zenith angle changes, some of the larger solar zenith angles, the altitude of the emissions going up because the sunlight, the solar EUV is stopping higher in the atmosphere, and that the pressure is lower there. The composition is different. So that it does make a difference in the emission. And you may have noticed it. I finally did myself and was wondering about the variation with solar zenith angle, at least in the Odin-2. It's not as apparent actually in the T-disk because it's certainly noisier, but in the Odin-2 it was noticeable had to scratch my head a little bit and finally realized that, oh yeah, it was really, the emissions coming from higher altitude, so that makes sense. But it wasn't immediately apparent to me when I looked at it. And the first notice this is subtle, but I finally caught on. So anyway, this just to show you here how the populations look. This is a theoretical curve here. I guess it's actually got doesn't have the dots on the theoretical curve. There is without the dots, but the others have the dots. But we're getting consistent results. Sarov has been doing this. He's been done some nice work on this. So now it's clear that we can, by fixing the parameters, we can use one parameter for the LBH bands rather than having to use 7. That decreases the number of parameters we have to use in that retrieval by about half, which makes a significant difference in the uncertainty, improvement in the certainty of the results. He's also been doing some stuff with solar eclipse that occurred in 2019. These are really some unique measurements, really interesting measurements. Just for this dashed region here is the conjugate point to the solid region. So there's really some interesting observations. It's a series of scans where we're able to watch how, as the eclipse goes across near sunset, we're later in this year, December, there's actually an eclipse that goes through basically around noon. So it'd be even really better observations than what we are able to do here. We have a longer term baseline to look at. So we will be looking at those also as a campaign. This is a good warm-up. This is really great to have this. But these are some really surprising observations. The stuff that's in the JGR paper that's under review is about the observations. Some of the analysis we've been doing more recently indicates that, at least we find that we can't get the models to show as much decrease as what we see. At least they don't want to give us that. So it's not clear why that's happening, but it is a result that we're getting out of some of the recent stuff. Okay, now let's go to the occultations. These, I find these, they're simple observations, but they really tell an interesting story that even I can follow. The blue lines here show you where the occultations occur. It's one of these two curves. Since the satellite position is fixed, the position of the occultations is also. So what we have from the occultations then is we have altitude information from each one, and by combining a bunch of them, we get some local time variation. You can look at that. So just looking at the altitude, you have the variation. Of course, it's fit to data is fit, and that start out with an a priori, but the a priori doesn't really matter much. This is from the IMSIS model, so what was used here. And systematically, Jerry found that he gets values in the range that are a bit lower by maybe 40–50% than what the model would predict, from IMSIS model would predict anyway. And in the 160, 170, 180 kilometer range, you should be getting really good results. It's really, basically, it is independent of the a priori values. It's a self-calibrating, essentially a self-calibrating measurement in the sense that it's a relative measurement. So you just have to watch how the brightness changes as a function of time, which is how it really is a function of altitude through the atmosphere. So that was one of the first things we noticed. More recently, he's done more analysis. If you take a lot of these observations, you can look at the local time variation. And again, it's a bit of a surprise that we see it, it's sort of different. You can see that there is an offset in the values here. These are on the same scale, so there's offset in the values, but there's also a difference in local time variation between these. So it's more prominent in the observations than what the IMSIS model is giving it, which is, of course, an empirical model. And I guess it's not really a great surprise that that the observation or the model doesn't do, could be off at 160 kilometers, 170 kilometers. This is one of the first times that we've had something where we can really start tying this down. That's actually part of the problem with these observations. Like, what do you compare against? There's not really any good observations down at those altitudes. Okay, let me just wrap up here. Just summarize that things are going well. The observing is data keeps coming every day. No gaps, almost no gaps. Just maybe a little bit here and there. It's basically it's merciless. The pace is so. Certainly I'm glad that the early 2021 that NASA has a dedicated GI program for ICON and gold. Certainly there's lots to do of analysis of this. The gold's been providing some, certainly been surprising and exciting impactful observations and insights. And the combination of the gold and ICON, I think, it'll be far more powerful than what either is alone. And if you want to learn more about these and have the opportunity, there is a Grand Challenge workshop that's being run virtually this year, concert, this CEDAR Grand Challenge workshop. So tune into that. And just, of course, have the link here for the special section. And with that, thank you.